lab reports you had to submit. And last time we couldn't solve a problem about the forces coming. So the model was rotating. So I haven't still looked at it, that why it is happening. And I will have a look at it maybe on Friday. We will solve the issue. So, but today what we will do is we will do damage in tensile model. And if time permits after the break, we will also deal with a little complicated model where we will introduce a crack, and we will see using damage if the crack, we can simulate crack propagation. So if we can fail the model and how do we fail it, those things we will understand. And after that, it probably, so I think we started, how many weeks have we covered so far, including this one? Anyone has any idea?
So 5 weeks maybe.
Including this, if it is 5 weeks, so then we have 2 more weeks to deal with this. And so we will do that crack propagation. We'll try to do this on Friday. We will see the results. And then I want to model a simple thing which has a little coding involved. So based on the Python script, you have to apply boundary conditions. So that we will do in the next week. And if we have one more week, then we will only discuss in the last week, and maybe we will have a mid-semester examination somewhere after that. Okay. So in damage, what we discussed was that the stiffness degrades. And if you remember, we had a small element, and that element was, so we should do it in the 3D model. Okay. So let us revive a little bit on. Let me find out where is whiteboard. So okay, so if you remember, in damage and in damage we learned that the stresses they go higher when the damage parameter is involved. So this is how we trick with the reality. So if we have to model, we have to find out some things which can. So what basically damage is that you have some discontinuity in the material, and this kind of discontinuity differs depending upon what kind of material it is and what is the temperature and surrounding environmental effects. So, and if you look at material, one way of looking at it, although it might sound philosophical, the atoms also behave like people in society. So some of them take load, some of them don't, some of them act as a rebel. So those we call defect because they're not following all the rules. Not all type of defects are like that. So the real continuum mechanics defect in ductile material at, let's say, at room temperature, where the material is ductile and we are talking about crystalline material. So one good example would be any BCC or FCC material, not not HCP. So as long as it is ductile, you will have three-dimensional voids, and these voids might be of different sizes. And we explained that if you cut a plane, then actual area will not be the area of the cross section of this cuboid, and therefore if the area changes by a factor omega, and omega here is not area change factor, it is the damage parameter. So it is supposed to take care of the 3D effect also. So this damage parameter will be causing, so there is less area for the same amount of force, so the stress has increased, and the stress has increased by this factor. So the new stress is a little higher than what you have applied, and this is happening because of damage, and the same can be reciprocated in the current Young's modulus or elastic modulus. Not sorry, it is not Young's modulus or elastic modulus, it is the stiffness of, so the slope of the stress strain curve, and that changes with this amount from the initial slope. So you remember this, goes up, goes down, and if you unload here, then the slope of this line and this line and this line is same, but after damage starts, it changes. And this also you have seen in the experiment of LCF, where the stiffness degradation was happening. So this is how damage is incorporated. When we apply it in the numerical scheme, then usually in metallic materials, damage starts after plastic deformation. So post plasticity, it starts. So plasticity starts usually without damage, and then the damage starts. The damage begins at some point where plasticity already prevails, and then it develops, it evolves, increases, and then causes failure. So in the numerical scheme, there can be different functions. So environmental effect, which might affect the amount of damage. So let us say if this is my tensile specimen, one section of the tensile specimen, so it can be larger than this, but we are here, and here you can divide it in small areas, in small volumes, and these small volumes, and the same what we are discussing here now, you can use similar thing in solving the problem I gave you for the project. So how would you model the probability of brittle fracture? That was the problem. So you can use this idea there also. So what am I doing is not finite element analysis. Also, it looks like finite element analysis. What I'm discussing now is theoretical. So what can be done is this whole thing, this whole specimen, I can divide it in these small cuboids, which actually would look like finite element elements. But I'm not doing any finite element calculation. I'm just taking a small piece from here, and this is my small piece. And in this small piece, I want to have all the property of the whole thing, which I have in this material. I want to have everything in here. So this small box represents the whole specimen. What do I call it? I call it reference volume element, because this volume element represents the whole thing. But the question is, does it? So depending upon the position, if I take one box from here, or if I take one box from here, or if I take one box from here, will it have same environment or not? if it doesn't have same environment? Can I impose generality in certain mathematical way so that depending upon whatever variation happens because of the position can be taken care of by the element. So this element then becomes independent of the position. So if I put this element here and I design the equations in such a way that if it is at the surface, it takes care of the effect what might appear at the surface. So let us have a look on the situation which might alter if we change the position. So what can happen is at the center usually, so if you go across the specimen, at the center here, you will have high constraint. So because of high constraint, you will have high stresses. Yeah. So at the surface, usually the stress is 0. And as you go in the center, the stress increases, and at the very center, the stress will be maximum. Why it is? Because this atom, so let us look at this atom, one single atom sitting at the center of the specimen, and imagine the whole specimen to be homogeneous. And then you are pulling the specimen, of course, in the upper direction and lower direction is fixed. If you are doing this, the material has to flow in the upward direction, and also it will be flowing in the downward direction because the same scenario is equivalent to this scenario. Yeah. So actually the material is flowing in both the direction, and because of symmetry, at what position of this specimen the material cannot flow in either direction, up or down. So because of symmetry, that point will be somewhere at the center, right? And then this center. So this center actually has flow in all the directions. But this atom, which is exactly at the center, is confused and it cannot go in any of the direction because of the symmetry. So at that center point, you have maximum amount of constraint. Yeah, constraint in the way that this material, the amount of material which is there, cannot flow in any direction. And so the only possibility for this atom is to get destroyed. So now instead of being an atom, if you imagine it to be a reference volume element, and if this reference volume element is at the center, then this reference volume element cannot flow in any direction. So the only possibility it has is to break down. Yeah. So the damage here will initiate first because of the constraint, and it will evolve much in a much higher way in comparison to any other element you take which is located away from the center, either on the upper side, lower side, or inside somewhere. So in any direction away from the center, this will have a different kinetics of damage. So the damage evolve at a different rate, and it will evolve. It will also start at a different time of the loading. So these things are changing because of the location. So in simple way, what I can say is this damage parameter will be a function of how much plasticity has happened. Of course, if effect of temperature will be there, but temperature can be reciprocated in the model by stress strain diagram. So the values of stress and true strain we are giving, so that so this is stress strain points which we give in the model should be the point of the temperature we want to simulate. So we conduct a tensile test at that temperature, whatever is the test temperature. And from that experiment, I take the stress strain values, change it to true stress, plastic strain, and then put it in the model. So then the temperature effect is already there. Apart from that, I can also do the test at certain, and we usually do the test at certain strain rate. But even then, even if you put the specimen, and we did it in our lab, you put the tensile specimen in the machine, and then you define a loading rate for this, which is, let's say, 0.5 millimeter per minute, millimeter per minute. So this is the amount of rate which we have defined. If the gauge length is 20, let's say if the gauge length is 20 millimeter, then what will be the strain rate for this specimen? Can any one of you calculate it? The strain rate is usually d epsilon by dt. So you can take it delta epsilon by delta t. Yeah. And what has been defined, what has been given to you is the displacement rate. So 0.5 millimeters, the specimen is moving per minute. If this is the displacement rate, the gauge length is 20 millimeter. Can you calculate the strain rate? Can any one of you calculate the strain rate? So you can do it in the break time. When we have a break, yeah, Suraj.
0.025.
0.025. And what is the unit?
Per minute, mm से डिवाइड हो जाएगा.
Oh,
Only.
okay. Yeah. So sounds good. I think it should be 10 to the power minus 4. 10 to the power minus 4 approximately in per second. Okay, so then you don't have to do it in the break. So this strain rate, so this remains constant in the experiment, but that doesn't mean that the strain rate in every reference volume is constant. It doesn't mean that, because you see that stresses are differing based on the location, and therefore strain is will also differ. So if you imagine it to be completely elastic material, then if the stress is increasing here maximum, so the strain will also be maximum there, and strain will also be minimum. If it has reached in plasticity, then also the plastic strain will be different. And it is not the elastic strain which causes or which alters the damage, because damage initiates and is dependent on plasticity, which is permanent deformation, because damage is also permanent. It is not going to get recovered. So it depends upon the plastic strain and by what amount the plastic strain is changing. So that we call the plastic strain rate. So instead of writing like this, the notation which is used is epsilon subscript PL, and a dot above it, it represents this. So we have also discussed that tensile problem in as far as we model it is a quasi-static problem. Quasi-static problem means that although there are changes happening, but they are so slow in terms of material response that it is time independent. So stress strain behavior of the material is not dependent on time. And then there is no inertia effect also. So if those things are not here, then what rate are we talking about? So this rate is not actual time of the test. It is actually the simulation time. If you remember, we go from 0 to 1. So just a second. So this is that plastic strain rate. So this plastic strain rate affects the damage parameter. And what else affects the damage parameter is the constraint, as we spoke of, that the constraint changes as you go away or move away location-wise, spatially in the specimen. So how do you measure this constraint? There are different parameters to measure the constraint, but a simple, very simple and very unique parameter is represented by small q and is a ratio of minus p by sigma mesus. Yeah. So sigma equivalent. So in abacus, it is represented by P, but actually in the theory, it is sigma hydrostatic divided by sigma equivalent is sigma mesus. I will write sigma mesus because you know what is sigma mesus. And sigma mesus and equivalent is the same thing. Sigma equivalent is the same thing. So in abacus, the hydrostatic stress is calculated in terms of pressure. So how this is different from hydrostatic stress? So hydrostatic stress usually is what you have along the diagonal. So whatever value you have here, and if these values are positive, then the hydrostatic stress. So if these values are positive and equal in amount, so let us put some value here. So let us put 10 megapascal, 10 megapascal, 10 megapascal, and rest are 0. So then it means what? That sigma 11 is equal to sigma 22 is equal to sigma 33 is equal to 10 megapascal. So imagine RDE. So you have 10, 10, and on what planes I have applied? On the top plane, applied on the side plane, which plane remains? So this is my x direction, this is my y direction, this is my z direction. So I have 10 megapascal here. So this element is getting stretched in all three directions, yeah, equally. So what will happen? Nothing will happen. There is no shear stress, so there will be no plasticity. It will just expand, so there will be a bulk modulus and there will be a volumetric strain. And this represents hydrostatic tension. So this thing is going to get, as a response to this, is going to get expanded volumetrically. So there will be a volumetric strain. The opposite of this is what abacus calculates. So the pressure is positive. The pressure is a positive value when it is compressive in nature. So it's exactly opposite of what is happening here. So instead of expansion, there will be a uniform compression on this reference volume element. And in that case, this will be a positive value for the pressure. So it's just a way of denoting things. So whatever abacus calculates in terms of pressure, if you multiply that by -1, you will get the value of sigma h, hydrostatic stress. Yeah. So hydrostatic stress and mesus, that ratio represents the triaxiality, we also call it. We also call it constraint, but constraint is a vague term. So the technical term for this is triaxiality. Okay. So how much triaxial stresses are available there? That is represented by this. So you can also have an understanding in this case that it is actually a ratio between how much hydrostatic stress is applied in terms of how much shearing is there, because sigma mesus actually represents the shear stresses in 3 dimensions. So this quantity basically means that how much hydrostatic stress component is there in comparison to the shear stresses. So that represents triaxiality, and damage parameter is a function of these two mostly. So for ductile metallic materials, ductile metallic crystalline material, we can define damage in terms of equivalent plastic strain rate and triaxiality. So if we have to define damage, how do we get these variations? So how do we know that the damage? So what is the relation of damage parameter with this and with this? So in order to get it experimentally, there so different experiments are performed usually. So you take a tensile specimen which has a notch in it, and you make different notches with different root radii, and each root radii would represent a different level of constant. So what you can do is you can simulate a simple tensile specimen with some amount of root radius. So it's basically is a U notch, and you do an elastic simulation and find out the value of Q. And you will see in the most area here, although Q will have a variation here also, but not too much. So you can take a range of Q here, and that Q will be specific for the root radii which you have given in the simulation. Then you change the root radius of the notch and do the elastic simulation again and calculate different triaxiality values for different tensile specimens. And for all those, you have different stress strain diagrams. Yeah, so you will have different amount of fracture strains. So basically what it means is that if you change the triaxiality, the material fails at different amount of strain. So that is somehow related to the damage. Yeah. So you will have different amount of fracture strains for these specimens, and this is the function which you have to provide in the simulation. So you have to provide the relation between triaxiality, fracture strain which you get from the experiment, and you can also calculate the equivalent plastic strain rate if you do an elastic plastic model for these conditions. Okay, but what we will do is we will simply trick it by defining the values of parameters which are required as 0. So we will give triaxiality value as 0, or we can give it some different value, it doesn't matter. Because if damage parameter is a function, or let's say I'm saying that the fracture strain is a function of strain rate or triaxiality. So I say that the fracture strain doesn't change with the triaxiality. So it remains constant, whatever is the value of triaxiality. Yeah. So if my fracture strain value is something, which is this. So let's say this is 0.2. Then what should be the value of triaxiality I should give? So triaxiality will have actually infinite values. This is similar to ideal plasticity. Or if I do the opposite, then what happens? So if I fix the triaxiality, then the fracture strain, no, but I have to fix the fracture strain. Then what is the value of triaxiality I should provide? So if I give the value of triaxiality as 0, what happens? So this is the point. And then, yeah, okay. So what we will do is, we will provide different values of fracture strain and triaxiality. So we will give the same value of fracture strain, 0.2, 0.2. I think only 2 points are good enough. And then here we will give a value of 0 and a value of 10. So it simply means, if 10 is here, it simply means that we are giving 2 points on the straight line which is parallel to the Q axis. That means it is independent of the triaxiality. So whatever is the value of triaxiality, the fracture strain is not going to change. Why I'm doing this? Because I do not have experimental results to obtain this kinetics. And so I'm making it independent of the triaxiality. Okay, so let us try this, and then we'll go for a break. So let us try this on our 3D model, which is this one. And I don't want to see rotation, so I will just fix it where I do not know, so I have to find out why it was rotating still. So we have defined Z symmetry, and it was rotating along the third axis. So I will create another boundary condition, and on which I will apply rotation. I'll take this thing, and I will apply UR3 is equal to 0, and I will. So this was not because of the initial state condition, because we couldn't stop rotation last time. So I don't know why it was rotating, but I'm stopping it by saying that this plane cannot rotate along the third direction. Hopefully it will work. So everything else remains the same, right? So we have stress strain behavior given to it. We have boundary condition applied to this. We just have to add the damage part in the material module. So none of you are speaking, so I'm just making sure that everything is audible, visible, and so far you understood everything.
Yes, sir.
Okay. So everything remains same. We have plasticity here, and then in damage, we have different models for different type of material. So what we are discussing is about ductile damage model for metals, for crystalline metals, usually BCC or FCC alloys. So I am choosing ductile damage, and here I have to define the amount of fracture strain. So I will put 0.2 here. Triaxiality I will put 0, and strain rate also I will put 0. So I'm making it independent of strain rate also. Strain rate, this strain rate is actually the equivalent plastic strain rate. How do I know this? I will tell you how do I know this a little later. And then, so this table usually works like we had here. So you keep on pressing enter and you create new row, or you keep it in Excel data and you can just put it here by pasting it. So again, I give 0.2, 0, 0. Hopefully I will not get any error message because I'm putting 0 values. I'm also not so sure about it, but we will see. And then, so this is the definition of when damage starts, when damage begins. Once damage begins, so this part I didn't discuss. Once damage begins, then the next question is that how does it evolve? Okay, so that is what we call, I'm still presenting. So that is what we call the kinetics of damage. So this is the point where we are defining the fracture strain value, the equivalent plastic strain rate relationship with it, and then what we are defining is stress triaxiality. So these 3 points are going to tell me when omega will be just greater than 0. Meaning, so omega sometimes also is represented as D because D is damage. So it means that exactly when in the RBE the damage initiates, the damage starts. So what does it mean on stress strain curve is simply that, so if my damage starts after this point, so damage just became greater than 0, and before this it was, so damage was less than equal to 0. So it cannot be less than 0 because that will be like superior element or something. So it can only be equal to 0. Damage less than 0 doesn't make any sense. So it is equal to 0 on the left hand side, and as soon as you cross this point, it is greater than 0. So what does it mean? It means you do n number of unloadings here, and you will have same slopes, and just beyond this point, if you do unloading, you will have different slope here. So stiffness will degrade after this, and degradation will continue. Yeah, but exactly here you might not find out significant amount of difference in the stiffness. So damage has just started. That is the part of damage initiation. And the second part is the kinetics, that how it evolves, how the damage builds in. So we know that damage is going to go from 0 to 1, right? And at some point it is going to initiate. So that point we have to define using this. But from 0 to 1, if something has to go from 0 to 1, so damage has to go from 0 to 1 with the simulation time. It can go like this, it can go like this, it can go like this, it can take any curve. Yeah. So what do we know about it, and how are we going to describe this? That which path this is going to take to know. So how are we going to describe that damage will take either this path or this path or this path to reach 1? Yeah. So again, to do this experimentally, you have to be very cumbersome. So, and then there will be a lot of error involved in it. One way of doing it is, and I'm not so well informed about this process, is called positron inhalation technique. So you bombard the specimen with positron particles, so the antiparticle of electron, and that can locate and define where are the voids in the material and what is the size of those. So depending upon that, you can calculate at different. So what are you doing is you're putting the tensile specimen in the machine, you're loading it, and you're also bombarding it with positrons, and then you're detecting the images, and you're seeing that at what point the small voids started forming and with what rate their sizes are increasing, and so on. So this is actually void volume fraction you're taking. So in the whole volume, how much is the volume of these small voids, and how is that void volume fraction is going to increase? So is it going to increase linearly? It is going to increase like this or like that, or whatever path. And from this information, you describe this behavior. This is one way of doing it. Another way of doing it is, again, you do the tensile specimen and load it. So you are loading it. So you are applying, let's say, so you have applied, let's say, 0.2 millimeters. You just pulled it 0.2 millimeters, and you make sure that the stress has gone beyond yield strength. So it is a permanent deformation. Once it is a permanent deformation, you stop the test. Okay, stop the test, cut it here. Well, actually, what you can do is you can actually load it to significant amount. So let us load it to 2 millimeters, and you observe what that the tensile specimen has actually necked. Yeah, you don't break it. Don't break the specimen. As soon as it has necked, you stop the test. Stop the test and cut it here, then cut it here, and cut it here, 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 and so on. And then look at under microscope each section. 1, 2, 3, 4, 5, 6, 7, 8. Each section you look at under the microscope. What you will see is where it has necked, you will have high amount of plastic strain. This you can calculate by doing finite element analysis. Don't bother about damage, just do finite element analysis, and you will see that how much plastic strain should be here, because you have this strain behavior. Okay, so from the finite elements, you know that if the structure is like this, how much is the value of stress, and at corresponding to that, what is the value of plastic strain. So you know at which plastic strain. So you look at that under scanning electron microscope, you will see the voids, right? And these voids will either look bright or dark, depending upon the field you're looking at. So there will be a contrast. So rest of the thing is continuum, and these are voids, and then you calculate the void volume area assume that it is also void volume fraction, and here is the error because of 2D to 3D conversion, and you cannot avoid it, but this is one of the ways how you put damage kinetics into the picture. Okay, there are other ways also. There are other techniques. One technique is you take the tensile specimen, you put two wires here, okay, and pass a constant amount of, so apply some voltage here, and depending upon the resistivity, you will have some amount of current in it, right? So basically, Ohm's law is applied, and R is rho L by A. This rho is not density, this rho is resistivity, which is a material property. Yeah. And so it depends upon the length of the specimen and the area of the specimen. And we know that when there will be damage, the area is going to change. And because of that, there will be a change in the calculated resistivity because we are not calculating area. So we will see a difference in the resistance. And this change in resistance can only be given by, can only be a representation of damage, because resistivity is a material property that is not going to change. Length, we know by what amount it is changing because we can see it, we can measure it. The damage which is happening inside, that we cannot measure. So we are not bothered about LA or rho. We are bothered about how much is the change in the resistance, and that is straight away related to the damage parameter. And you can do this, and you can also find out the kinetics. So that is the part of how we get the kinetics. But in our model, we will also have a very simple representation of damage kinetics. So what we will do is, so in order to define that part, you have to go to sub option, go to damage evolution, and here displacement means you can give amount of displacement in the element. So one element is displaced by certain amount, and that you define as the failure. Okay, this softening is about the stiffness degradation. It is not the softening which happens after yielding. Okay, so I will have to explain this again. So still presenting. So the things which we have to understand is displacement and the softening, and what else was there? Degradation and displacement at failure. Displacement at failure and degradation. So displacement is the type which Abacus is asking for. So it is asking whether you are defining the damage evolution in terms of displacement of the element. Okay, so if I take 2D element, then it is talking about either the displacement in this direction or in this direction, or net resultant displacement. So what should be the amount of displacement, and depending upon that, the failure is designed. So this is one type. Another type is the type of energy. So you define the damage in terms of energy, and we will do it in terms of energy. But displacement is an option. So that is one type of defining damage evolution. Second is the softening. This softening is not the strain hardening, strain softening, what we have discussed. It's just strain curve. So it is not this. So this is hardening, this is softening, and we are not talking about this here. This is different. This is also in stress strain curve, which we have spoke about, but not after yielding. So you see, it goes like this until UTS, and after that it starts decreasing. This is also softening. And this softening is happening because of damage. And this is so common because, so we don't say that there is any hardening which can happen, but in polymers it will go up. So in metallic materials, it is a softening which is because of damage, and this is the softening which is being spoken about here. And in this softening, you have to define that how you want to define this part of the curve, how you want to define this. So do you want to define this softening in terms of linear equation, or you want to define it in an exponential form of equation, or you want to define it in your own unique way by defining different points along the axis of damage kinetics. So basically you will have to give these data points, and these data points you can provide in the form of a table. Okay, the same thing you can do in the energy mode also. So then in the displacement mode, you choose displacement, you choose what kind of softening you want to define by linear equation, exponential equation, or table, and then you have to define what is the displacement value at which the RBE, the element, will fail. Okay, so if I write 0.2, then as soon as this element reaches a value of 0.2, this element will simply stop bearing any load. No equation will be solved for this element, and this element will be removed from the total assembly of finite element analysis. So this will be just lost, gone, disappeared. Okay, so the same thing you can do in terms of energy. The difference will be, instead of defining displacement at the failure, you will have to define what is the energy at the failure. And this energy is simple because we can calculate, we can find out this energy either by taking the area of the tensile stress strain curve, or you can do fracture toughness testing and you can find out how much is the energy, and that energy is readily available also in the literature. So we can use that also. And if you want to use displacement, you will have to change the information from energy to displacement, either that, or you will have to do the experiment and find out that at which displacement the material is failing. Another important part is that now let us look at this RVE. So this is the reference volume element, and these information which I'm talking about here will help you a lot in the project which you have described for the brittle fracture. Only thing is I'm discussing ductile and you will be giving a solution on brittle fracture. But of course you can have your own solution, and that's what I want. So let us look at this RVE, and we are defining damage. Damage has increased, so it has started. So that means it is greater than 0, right? And then what do you think it will fail at which point? So let me answer it for you. You don't have to wait until damage reaches 1. Okay? Until damage reaches 1, the material will fail is not true. Material can also fail as soon as the damage reaches a value of 0.7. Because what does it actually mean is that you have bigger voids and 70% of the volume is taken by the voids and only 30% remains. So do you think 30% of this reference volume element is sufficient to take the load? And also it is realized in our stress strain diagram of a tensile specimen that this stress increases and then it goes to the maximum and then it starts dropping. But you don't see a stress strain diagram which usually goes like this till the stress becomes 0 and then it fails. It never happens. Never happens. It breaks somewhere between. That means at this point, the material was not able to bear anymore and it just broke into 2 pieces. Or at this point. It never reached the point where the stress bearing capacity completely became 0. That means damage became 100%. It never happens. So actually your element or your material also in reality never goes to the extent where damage is completely 0. Imagine it in this way, that a human person cannot sustain to the last point of complete organ failure. So at some point, the person will have to lose, because you cannot be alive until everything is not working. One crucial part or several moderately crucial parts stop working, and then your capacity of being alive is gone. It is comparable to that. Okay, so now let us go back. So that was a little theory, and now we do it. So am I sharing? No. Okay. So here I can choose displacement, I can choose energy. So I choose energy, and then you see here linear exponential tabular. It doesn't. So unless you have experimental data, you can choose anything. But remember that this softening linear exponential tabular is the relation between damage parameter and the loading, so the time of the simulation. So it will not be reflected in the stress strain diagram. So if you are choosing an exponential variation of the damage parameter, it will not be reflected in the stress strain softening part. So that part doesn't have to be exponential or linear, because that is not straightforward coming from the kinetics of the damage. Okay. So we choose linear, and then here maximum multiplicative, we don't have to go in that. So I will keep it at maximum. And fracture energy, I have to give, it is a metallic material. So usually I think fracture would happen approximately at 20 kilojoule per meter square, which will be Newton per millimeter. And our forces are in Newton, dimensions are in millimeter. So to be at a safer side, I will put 10. Because 20, if it takes too long time, then we cannot solve it. So we will see if it fractures very fast, then we will of course change this value. So hopefully everything will work, and then you can. So these are little complication. If you want to simulate something, if you have a heat flow, temperature is changing, then you can also put things as a function of temperature. So now I have given all the information about damage evolution. And so damage initiation evolution is given. This is the part which I had to change in the material property. Apart from that, there are other things which I must do. So I go to mesh, and then I select on the type, and then I take it, and then so I have taken the whole specimen. I didn't have to do it. What I could have done is I could have just defined damage in this small partition which I have made. Yeah, because tensile specimen will have to break somewhere close to the center, not in the part which is beyond the constrained area. Okay. And why? Because damage usually causes a mesh dependency, and I have a change in element size. So I shouldn't actually provide damage here, because the bigger elements are not so accurate as the finer elements. And this might become problematic, but I don't think our model is so complicated. So I'll just put damage everywhere in the system. So the material is provided in the whole. So the material is assigned to the whole body. So that means damage is also assigned to the whole body. So here everything remains the same. So 3D stress, linear shape function, and standard. That means implicit algorithm we are doing. Everything else remains the same. Here you have to scroll down, and you have to look for element deletion. Usually it is use default value, but you make it sure by clicking on yes. Maximum degradation, you can choose a default value, but if you have experimental data, as I explained earlier, the element can fail even at 70% of the degradation. So if you want to do that, if you have that information, that 70% degradation is enough for the element to get deleted, so you write 0.7. Okay. If you do not know this value, use default value, and default value is simply this. This is the default value. Okay. So I would put 0.9, and I will specify it, and this is the only thing which you have to change apart from changing the material. And then you have to go to the field output, and in the field output, so everything what you selected is okay, but you have to select the status in the state field user time subcategory. To choose status defines some failure and plasticity model view mat is a different thing. So this will define if the element has failed or not. And the element deletion, what we just did in the mesh, will make sure that the elements get deleted from the model. And these we are not calculating, so we shouldn't call for it. If you shouldn't call for anything which you are not calculating, because that will cause unnecessary burden on the simulation. So the only thing is this status I should have, and yeah, I should also have stiffness degradation, SDEG. So where is it? It should be in the fracture. So ST, scalar stiffness degradation value. So this we want, and then OK, and everything is good. Let us submit the job. Before submitting, let us rename it and call it damage. And OK. Setting the work directory, it is already there. So submit it. The independent, so there is some error. Independent variable must be arranged in ascending order. And I'm sure this is what is wrong with, we have defined in the damage table. Independent variable must be arranged in the ascending order. Strain output, blah, blah, blah. Output request TE have not asked for. This is because of default values. So independent variable in ascending order. So that means, okay. So I cannot change the value of fracture strain. But if I change it, then this line will have a linear slope. So maybe I do this. So let us see if this solves the issue or not. It is not solving the issue. Warning. Execution terminated, warning. Where's the error? It's not error. Appearing line image pointing with this. Okay. So if I define a higher value, so what have I done? I have to find two different. Oh, that was wrong. So what I discussed, I didn't do that. You have to give 10, you have to give whatever value, 1000. So remember, on the same straight line, I have to give 2 points so that it becomes parallel. I didn't do it. I defined exactly two same points. So I just repeated what I wrote in the first row. So warning, but the job has been, so the calculation has started. Yeah, these warnings are not because of our problem, except this one. Boundary conditions are specified, and yeah, this is coming because I have imposed that rotation thing, because our model was rotating. So it is saying that it is inactive, so there is no use of it. But let us see, it still rotates. So 0.3 and 0.5. So half of the simulation is done. Let us look at the results. And what has happened? Nothing has happened. Are we not going into? Yeah, it is 549. So let's start it. Why is it plane? Huh? Why is it no? What plane is this? XY is the cross section. I look at YZ plane. Not like this. Z will be not like this. Yeah, XZ. Okay. And I want to be standing in. So this is means what is the value of plastic strain? Why do we not have plastic strain? Why do we not have plastic strain? It's gone very small value. Very small value. So stiffness degradation has not yet started. Why it has not started? Because my damage initiation point is where? I think simulation has ended. Yeah. And the damage didn't start because my initiation point is too far. So I want a fracture strain value of 0.2. How much strain are we getting? How much strain are we getting? We are getting from, we want 0.2 and this is like 0.03. 0.03. So either I change the amount of displacement I'm applying or I change the initiation value to 0.03. 0.03 will be how much? 10 points. Yeah. So 0.03. So it should just start, but it will not fail because. So let us also increase the amount of displacement I'm applying. Symmetry. So here instead of 3, put a 3.4. Okay, 1 more millimeter. And submit. Okay. It will not 3.3 over. This is 0.025 so far. It's only 0.3. It might reach. What happened? Oh, error. Aborted. Fixed time increment. Yeah, that cannot happen in damage. Fixed time increment is too much pressure. So automatic 9 1 0 1. It is already terminated, but still showing running. Okay, 3D damage. Error again. No, that is different job. It's distorted. First increment, and this is very slow. Second increment should look after fifth increment, so 0.5 at least. So there is some convergence issue to maintain, but then convergence is assured. So now we know still we don't have 0.1 time increment. Approximately 0.025. 0.3, 0.3, 0.34. 0.34. So you see here, this iteration didn't converge. So another was tried at the same time point. So this is why you see 1U. It goes to 1U, 2U, 3U, 4U. Then after usually 4, 5 U's, it is over. Depending upon the second. So let's go on to still 0.34. Doesn't move. Okay. Maybe it will take some time. Let us have a look at the results so far. So stresses are a little lower, but damage has not yet started. And the plastic strain is 0.027, so it is just reaching the damage initiation value, which is 0.03. So 0.03. Any further increment has not happened. It is taking too much time. I think it will fail. Will abort. It is taking too much time. So numerical singularity when processing node number this. Okay. So we can have a look, we can have a break, and we can come back and have a look at this model. Let me see if it is rotating. It looks like it is rotating still. So extra boundary condition to stop that rotation has not worked. It is still rotating. Yeah. Okay, all right. I hope I was audible so far and you guys didn't sleep. So,
Yes, sir.
didn't sleep? Okay.
No, sir.
I'm sure it will abort. This behavior is not good. But I'll be happy if it doesn't. So we take a break till 11 a.m. We will be back again. This is the message from Usha. Okay. So we will come back at 11. We'll see what is happening. I don't think we can do fracture modeling today, but we will see what we can do today. Because in 1 hour, we cannot do fracture modeling. but we can try, no issues. Okay, so we meet at 11. You take a break till 11. We meet again. Okay.
Okay.
Okay, sir.
Okay.